Hi, welcome to the fourth trigonometric tutorial. Today's tutorial is titled Complex Identities. We will begin by looking at the square identity. We will then move on to the compound angle identities. We'll move on to the double angles. And lastly, we will look at proving left-hand side is equal to right-hand side. In terms of what you need to know, you need to be familiar with your grade 10 work. You also need to have gone through the first three trigonometric tutorials. The first basic identity I want to go through is that of tan. Tan theta is equal to sine theta over cos theta. Let us look at how that happens. Remember that tan theta is equal to y over x. Sine theta is equals to y over r, and cos theta is equal to x over r. If we say y over x sine theta, y over r sine theta divided by x over r, which is cos theta, we're going to get y over r divided by x over r, which is equal to y over r times by r over x. The r's will cancel, and that will leave us with y over x. And remember, y over x is the same as tan theta. The next identity I want to go through is called the square identity. The square identity very simply states sine squared theta plus cos squared theta is equal to 1. This is applicable for any variable angle we may plug in for theta. For example, sine squared x plus cos squared x is equal to 1, or even for number values. Sine squared 30 degrees plus cos squared 30 degrees will equal 1. Let us now look at the compound angles and the double angles. Please note that this is a section you do need to go through. I wouldn't say you need to memorize it because it is in all of the formula sheets that you will have, but understand how it works. The first compound angle looks like this. Sine of theta plus beta is going to equal sine of theta multiplied by cos beta plus cos theta multiplied by sine beta. Sine of theta minus beta equals sine of theta times cos beta minus cos of theta times sine of beta. Cos of alpha plus beta is equal to cos of alpha times cos of beta minus sine of alpha times sine of beta. Cos of alpha minus beta is equal to cos of alpha times cos beta plus sine alpha times sine beta. Remember that even though in these examples I've used theta, beta and alpha, you can use any variable in there, and again you can use number values. For example, if I start out with cos 15 degrees, I can turn that into cos 45 degrees minus 30 degrees, which will equal cos 45 multiplied by cos 30 plus sine 45 multiplied by sine 30. We are now going to look at double angles. Double angles are derived using compound angle formula. The first double angle we are going to look at is sine 2 theta. Sine 2 theta is equal to 2 sine theta cos theta. That comes about using the compound angle formula sine theta plus beta, except because it's 2 theta, we're going to use sine of theta plus theta. Sine of theta plus theta will equal sine of theta times cos theta plus cos theta times sine theta, which is going to equal 2 sine theta cos theta. Similarly, the double angle formula for cos 2 theta has been derived. Cos 2 theta is special in a way that it has 3 possible outcomes. The first possible outcome is cos squared theta minus sine squared theta. The second possibility is 2 cos squared theta minus 1. And the third possibility is 1 minus 2 sine squared theta. Let us now look at a few basic examples to illustrate the application of what we've done thus far. The first one we're going to be looking at is tan of theta. I'm going to use tan of 60 degrees. Now the reason you're going to see that through all of these examples, I'm going to be using special angles. The reason being is they're very easy to work with and they give us fixed answers. Tan of 60 in theory should equal sine of 60 divided by cos of 60, sine over cos. Let's see how that turns out. We know from our special angles that tan of 60 degrees, let's just do our special angles again, 90, 60, 45, 30 and 0, x values, y values, 0, 1, root 2, root 3, 2, 2, root 3, root 2, 1, 0, r is equal to 2. Now tan is y over x. Of 60 degrees, y is root 3 and x is 1. Let's see what happens to this side. We have sine 60 over cos 60. You agree that's the same as saying sine 60 divided by cos 60. Sine of 60 is root 3 over 2 divided by cos of 60, which is x over r, 1 over 2. Tip in times, I turn that divide into a multiply and I swap those two around. Those cancel, which gives us an answer of root 3 over 1, which is the same as tan of 60. The second example I'm going to look at is that of the square identity sine squared x plus cos squared x is equal to 1. Now let's look at that. I'm going to work with sine squared of 30 degrees plus cos squared of 30 degrees, and let's see what that is going to equal. Sine squared 30, sine of 30 from the special angles is equal to 1 over 2. Sine squared 30 is 1 over 2 squared. Plus cos squared of 30, cos of 30 is root 3 over 2 squared. That's going to give us 1 over 2 squared is equal to 1 over 4. Root 3 squared is 3, 2 squared is 4, 1 plus 3, or rather 1 over 4 plus 3 over 4, common denominator. So I can add the numerators. 1 plus 3 is 4, 4 over 4 is equal to 1. That means that sine squared 30, or rather not 30, sine squared x plus cos squared x, those have to be the same, is equal to 1. The third example I'm going to look at is that of sine 75 degrees. Now I'm going to try and use special angles to solve this one, and compound angles. Sine 75 is the same as sine of 45 degrees plus 30 degrees. Now sine of a plus b we know is equal to sine of a times cos of b, which in this case is 30 degrees, plus cos a times sine of b. Sine of 45 from our special angles we know is equal to root 2 over 2 multiplied by cos 30, which is root 3 over 2, plus cos of 45 is root 2 over 2 multiplied by sine 30, which is 1 over 2. 2 times 2 is 4. Root 2 times root 3, we can make it root 6, but I'm going to leave it as root 2 times root 3, and you're going to see why. 2 times 2 is 4. Root 2 times 1 is root 2. Denominators are the same, which means that I can add the exponents. When I'm adding the exponents, I've got a common factor of root 2, which will leave me with root 3 plus 1. And that is what sine of 75 degrees is equal to. You can check that on a calculator. If this is what sine of 75 is equal to, doesn't that mean that sine 75 is almost a special angle? Because it will always have this ratio. Keep that in mind. The next one I'm going to look at number 4 is going, well, not number 4, but rather the next one, the next example that I'm going to use, also compound angles, sine of 15 degrees. Now sine of 15 is the same as sine of 45 degrees minus 30 degrees. Sine of 45 minus 30 is the same as sine A times cos B minus cos A times sine of B. Sine of 45 is root 2 over 2 multiplied by cos of 30, which is root 3 over 2, minus cos 45, which is again root 2 over 2, multiplied by sine 30, 1 over 2. That's going to give us root 2 times root 3 over 4 minus root 2 over 4, which is going to give us again common factor of root 2, except now compared to the previous example, it's not root 3 plus 1, it's root 3 minus 1 all over 4. Root 3 minus 1. Because the common factor of root 2, I took it out, which left me with root 3 minus 1. The next example we're going to use is cos of 75 degrees. Cos of 75 is the same as cos of 45 degrees plus 30 degrees. Cos A plus B. Now we know that cos A plus B is equal to cos A, which is cos 45, times cos B, cos of 30, minus sine A times sine B. That's going to equal cos 45 is root 2 over 2 multiplied by cos 30, which is root 3 over 2, minus sine 45 is root 2 over 2 times sine 30, which is 1 over 2. This is going to give us root 2 times root 3, I'm just going to leave it as that, over 4 minus root 2 over 4, common factor of root 2, which will leave us with root 2 multiplied by root 3 minus 1 over 4, and that's the answer. The last one I'm going to look at is cos of 15 degrees. cos of 15 is equal to cos of 45 degrees minus 30 degrees, which is equal to, now cos A minus B is equal to cos A times cos B plus sine A times sine B, which is going to equal root 2 over 2 multiplied by root 3 over 2 plus sine 45, which is again root 2 over 2 multiplied by 1 over 2 sine 30, which is equal to root 2 times root 3 over 4 plus root 2 over 4, which gives us an answer of root 2 as a common factor, root 3 plus 1 over 4. And that's what cos 15 is equal to. Now I just used these examples to show you an illustration of how we could break up angles or build up angles using compound angle identities. But there's something else that comes out of all of these. Have you noticed that this answer is very similar in all of the examples? Let's look at it carefully. First one we looked at was that of sine 75. Sine 75 degrees gave us an answer Sine 75 degrees gave us an answer of root 2 times root 3 plus 1 over 4. Sine of 15 degrees gave us an answer of root 2 times root 3 minus 1 over 4. Cos 75 degrees gave us an answer of root 2 times I'm just looking for my transparencies here. Cos 75 degrees gave us an answer of root 2 times root 3 minus 1 all over 4, and cos of 15 degrees gave us an answer of root 2 times root 3 plus 1 all over 4. Just keep a note of this. Now notice that sine 15 and cos 75 are the same answers, and that makes sense because sine 15 is the same as sine of 90 minus 75, which is the same as cos of 75. So sine 15 and cos 75 gave us the same answer of root 2 times root 3 minus 1 all over 4. And sine 75 and cos 15 gave us the same answers of root 2 times root 3 plus 1 over 4. If you want to remember that, you're welcome to. Alternatively, whenever you have a 75 or 15 degrees, you can break it up using compound angles and special angles. The next example and one of the last examples we're going to look at is sine of 2 theta. I'm going to work with sine of 60 degrees. Now we know from the outset that sine of 60 degrees is the same as root 3 over 2. Sine of 60 degrees, sine of 2 theta, sine of 60 degrees is the same as sine of 2 times 30 degrees. Now sine of 2 theta we know is equal to 2 sine theta cos theta. But it's not theta in this case, it's 30 degrees. 2 times sine of 30 would be 2 times 1 over 2. Cos of 30 is root 3 over 2. 2 times a half is 1 times root 3 over 2 is just root 3 over 2, which is the exact same thing as sine of 60. This is just an application of that. Most of the time though, you will have it in the form sine of 2 theta, which then becomes 2 sine theta times cos theta. The final example I'm going to look at is that of cos 2 theta. Again, I'm going to use cos 2 times 30 degrees. Now cos of 2 times 30 is the same as cos of 60, which should equal a half. Now we know that cos of 2 theta has got 3 different distinct identities. The first one being cos squared theta, so in this case cos squared 30 degrees minus sine squared 30. Cos of 30 is equal to root 3 over 2, but it's cos squared, so it's root 3 over 2 squared minus 1 over 2 squared, which is equal to 3 over 4 minus 1 over 4. 3 minus 1 is 2 over 4, which is the same as 1 over 2, which is exactly the same thing that we know it should equal. Now you'll notice that for cos 2 theta there are 2 other identities, the one being 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. The reason for that is that sine squared theta this here could be also, or rather could also be 1 minus cos squared theta, and cos squared 30 degrees could also be 1 minus sine squared theta. So it could go either way, but all of the answers would come to the same thing of a half in this case, because we used 60 degrees. We are now going to look at solving identities, or rather proving that the left hand side is equal to the right hand side. There are 3 rules that I want you to follow when doing these type of calculations. The first rule is convert everything to sine and cos. Specifically, look at 10. Take all of your 10s that are in your equation and convert it to sine over cos. Rule 2, start with the more difficult side. Usually you have either the left hand side, which is quite drawn out, is equals to a very small expression on the right hand side, or the other way around. Start off with the difficult one and try and simplify that. Also, convert all of the double and compound angles to smaller simplified angles. And thirdly, be creative. Manipulate either of the sides of the equation or both sides of the equation if you need to, and try new things out all the time. Take 1 for example, maybe convert it to sine squared theta plus cos squared, or something like that. But be creative, try different things all the time. The example I'm going to use says prove the following identity, and the identity reads 1 minus cos 2x multiplied by 1 plus 1 over 10 squared x divided by 1 over cos x multiplied by sine of 2x. And I need to prove that that is equal to 1 over sine x. Now, I'm going to start off with the side that looks most difficult. Most people would agree that the left-hand side is the more difficult side, so I'm going to start with that. 1 minus cos 2x, I'm going to turn that into 1 minus the first cos 2x is equal to, there are three possibilities. The one possibility is cos squared x minus sine squared x. The other possibility is 1 minus 2 cos squared x, or 1 minus 2 sine squared x, or 2 sine squared x minus 1. Although there are three possibilities, I always like to start with cos squared x minus sine squared x, because this one is the easiest to manipulate further, or rather it's the most noticeable. So assume that there's only one real identity for cos 2x as opposed to the three that do exist. 1 plus 10 squared, 1 plus 1 over 10 squared x. Now think about this. 1 over 10x is the same as 1 over sine x over cos x, which is equal to cos x over sine x, right? The same reason 1 over 2 over 3 is equal to 3 over 2. So 1 over 10 squared x will be the same as cos squared x over sine squared x. It's all of that divided by 1 over cos x, let's leave it for now as 1 over cos x, multiplied by sine 2x is equal to 2 sine x times cos x, and that's over 1. The reason I'm doing that is because it's multiplied by that. Now, the next step I'm going to take, I'm going to leave this for now as 1 minus cos squared x plus sine squared x. The reason it became plus is because a minus times a minus. And it's all of that multiplied by 1 plus cos squared x over sine squared x. Isn't 1 the same as sine squared x over sine squared x, common denominator? That means that that will read sine squared x plus cos squared x all over sine squared x. And this is our numerator. We've now got to get our denominator, or rather we've got to write down our denominator. So it's all of that divided by 1 times that is going to be 2 sine x cos x over cos x. The cos x's will cancel, so my denominator will just be 2 sine x over 1, or 2 sine x. That's going to equal, now sine squared x plus cos squared x is going to give us 1. 1 over sine squared x multiplied by something. I'm going to change that 1 into cos squared x plus sine squared x minus cos squared x plus sine squared x multiplied by sine squared x times plus cos squared x is equal to 1 over sine squared x stays there, all over 2 sine x. Now I'm not too sure if this is the right thing, I just know that what I've done is correct. What I mean by that is 1 is definitely equal to cos squared x plus sine squared x. Sine squared x plus cos squared x is definitely equal to 1. So mathematically I'm correct. Whether this is going to be the most efficient way of getting to my right hand side, I don't know. But it definitely is going to get me there eventually, if I carry on doing mathematically correct transformations. Cos squared x minus cos squared x cancels each other out. Sine squared x plus sine squared x is equal to 2 sine squared x multiplied by 1 over sine squared x. Look at this. Times by 1 over sine squared x. That's over 1, isn't it? We've still got it all over 2 sine x. Wouldn't that and that cancel? To give us an answer of 2 over 2 sine x. Common factor of 2, which leaves us with 1 over sine x, which is equal to the right hand side, which is exactly where we were headed. Now notice I tried a number of different things and I just carried on solving it according to mathematic principles, and I eventually did come to my right hand side. There might have been an easier way of doing this, I don't know. I want you to have a go at the following exercise. Press pause on your DVD player, and when you return we'll go through it together. The first example I gave you to do read 10 of x multiplied by 1 minus sine squared x minus cos squared x all over sine squared x minus cos squared x is equal to cos x over sine x plus cos x. This one here, again, I'm going to have to start on the left hand side. 10x is equal to sine x over cos x. 1 minus sine squared x is equal to cos squared x minus cos squared x divided by sine squared x minus cos squared x. This here, in fact, I think this one here I'm going to leave it as is for now. Yeah, let's leave this as is for now, as sine squared x minus cos squared x. We'll come to that a little bit later on, remembering what our right hand side looks like. Okay, next step I'm going to do cos squared x, sine x over cos x times cos squared x. Wouldn't 1 cos x cancel with one of those to leave us with just sine x times cos x minus cos squared x, all of that divided by sine squared x minus cos squared x. What I'm now going to do is, from the top I'm going to take out a common factor of cos x. That's going to give me sine x minus cos x at the top. Aha, look at this. Isn't this in algebra called difference of two squares? A squared minus b squared, that's equal to a plus b, a minus b. So this can become sine x minus cos x multiplied by sine x plus cos x. This and this cancel to leave us with an answer of cos x over sine x plus cos x, which is equal to my right hand side. The next one we're going to be looking at is sine x minus sine x times cos x divided by cos x minus, open bracket, 1 minus sine squared x is equal to tan of x. Again, we're going to start off left hand side. Sine x minus sine x times cos x, I'm going to take out a common factor of sine x. That will give me 1 minus cos x. The denominator, I'm going to turn that into, I'm going to leave that as cos x minus 1 minus sine squared x. Isn't that the same as cos squared x? Because remember, cos squared plus sine squared is equal to 1. That means that cos squared is equal to 1 minus sine squared, which is what we have happening over there. From the bottom, rather the denominator, I'm going to take out a common factor of cos x to leave me with 1 minus cos x. That and that cancels. Sine x over cos x is equal to 10x, which is equal to the right hand side. The next one we're looking at reads 1 over sine x minus cos x over sine x, all of that squared, and we need to prove that it's equal to 1 minus cos x over 1 plus cos x. I would suggest we start with the left hand side again. Now the left hand side does look like a bit of a nasty one. Let's not square it at first. We're still going to keep it squared, but we've got a common denominator of sine x. So can't that become 1 minus cos x all over sine x squared? Now we can square it. 1 minus cos x squared is going to be 1. Now remember this, 1 minus x squared, or let's rather use, to avoid confusion, 1 minus a squared. That's going to equal 1 minus 2a plus a squared, because it's 1 minus a multiplied by 1 minus a. 1 times 1 is 1, minus a outer inner is minus 2a. Minus a times minus a is plus a squared, right? Using that same concept, we're going to apply it here, except instead of a, we're going to have cos x. So that's going to become 1 minus 2 cos x plus cos squared x over sine x squared is sine squared x. Now, this does look nasty. What I'm going to do, remember that my right hand side has got a 1 plus cos x in it. In the denominator, right? Sine squared x, isn't that the same as 1 minus cos squared x? So I'm going to turn the denominator, I'm going to turn it into 1 minus cos squared x. And I'm going to show you why I did that later on. The numerator, actually look at this. 1 minus cos squared x, isn't that the difference of two squares? 1 minus a squared is equal to 1 plus a times 1 minus a. So 1 minus cos squared x, that can become 1 plus cos x multiplied by 1 minus cos x. Alright, so I made a mistake here, because 1 minus, at the top I've got 1. Before I went to go and square it out, I didn't need to. I could have left it as 1 minus cos x all squared, because now look at this. Let's imagine that I've got a squared over b times a. A would cancel, so that would leave us, that would cancel with one of those, so that would leave us with 1 minus cos x over 1 plus cos x, which is equal to the right hand side. Now please note that I haven't pre-prepared these examples. The reason I didn't pre-prepare these examples is so that you could see that you have to sometimes go through different steps, and you've sometimes got to make mistakes the way I did. Well, not mistakes, but you don't always come to the right answer or the right sort of methodology immediately, but continue looking at your right hand side and see how you can find a link. I had to do that here, and so in the example I did, this top step was totally irrelevant. I could have just left it as 1 minus cos x all squared over sine squared x, 1 minus cos squared x. Use your imagination, be creative. You don't have to follow. There is no one way of doing it. The next one I gave you to do read cos 2x over cos squared x is equal to 1 plus 10x multiplied by 1 minus 10x. This one is unique in that I can work at it from both directions. I'm going to start working with this one from the right hand side. Right hand side is going to equal, first before I turn the 10x into sine x over cos x, I'm going to multiply this out, difference of two squares, that's going to become 1 minus 10 squared x. 1 minus 10 squared x is the same as 1 minus sine squared x over cos squared x. 10x is sine x over cos x. This is going to give us cos squared x minus sine squared x over cos squared x. Cos squared x minus sine squared x, isn't that equal to cos 2x over cos squared x, which is equal to the left hand side. Now, if you don't like going backwards from the balance of the equation to the start, for example, from cos squared x minus sine squared x to cos 2x, what you could have done in this case was you could have stopped your right hand side there. Right? Now start with your left hand side. You could have said left hand side is equal to cos 2x over cos squared x. Now cos 2x we know is the same as cos squared x minus sine squared x over cos squared x, which means that they are now equal to each other. It is possible to work with both left hand side and right hand side, but don't try and do it at the same time. First go through right hand side or left hand side up until a point you're comfortable with, then do the other side. Number 5 is quite an interesting one. It says 4 sine x times cos cubed x minus 4 cos x times sine cubed x is equal to sine 4x. Looking at this one here, most people would say that this is the more complicated side. If you try to work it out using this side, or rather starting out left hand side, you would have got into a bit of a tangle first before really coming to an answer. If not, congratulations. I'm going to start this one out by looking at the right hand side. The right hand side I think is actually more complicated. Sine 4x, look at this, all of these are in the form single x. This is sine 4x. Now isn't sine 4x the same as sine of 2 times 2x? Sine of 2 times 2x, that's equal to 2 sine 2x times cos 2x. But those two can be simplified. That's going to give me 2 sine 2x is equal to 2 sine x times cos x multiplied by cos 2x. I'm going to turn that for now into cos squared x minus sine squared x. That's going to equal 2 times 2 is 4 sine x cos x multiplied by cos squared x minus sine squared x. I'm going to leave that as cos squared x minus sine squared x, and I'm going to leave that in brackets. Now let us look at the left hand side. Remember, now we are working with the left hand side, but we are trying to bring it to this. From the left hand side, can't I take out a common factor of 4 sine x cos x? Four sine x cos x can be taken out as a common factor, and that will leave me with cos squared x minus sine squared x. Isn't this equal to this? That means that left hand side is equal to right hand side. Number 6 said cos x over sine x minus 1 minus 1 over tan x minus 1 over cos x times sine x is equal to negative 1 over cos x. This one here we can clearly see we're going to start on the left hand side. I'm going to leave the cos x as cos x for now. Sine x minus 1, let's just leave it as is, minus 1, leave it as is, over tan x will become sine x over cos x minus 1 over cos x times sine of x. Again, I'm going to leave the first term as is. The 1 I'm going to leave as is for now. Common denominator here is going to be cos x sine x. What did I have to multiply this by to make it cos x sine x? I had to multiply it by sine x. What I do to the bottom, I do to the top. So that will leave me with sine squared x minus 1 over cos x times sine of x. What I'm now going to do, still this is going to stay as cos x over, use a new transparency, that's going to remain cos x over sine x minus 1 for now, minus 1 over sine squared x minus 1. That can become either sine x plus 1 times sine x minus 1, difference of 2 squares, sine x plus 1 over sine x minus 1, and it's that divided by cos x times sine of x. This one we're still leaving as cos x over sine x minus 1 minus. Now, think about this. 1 over 3 over 2 is the same as 2 over 3, correct? So 1 over that is the same as cos x times sine x over sine x plus 1 times sine x minus 1. Common denominator of sine x minus 1 times sine x plus 1 means that to the numerator I've got to multiply it by sine x plus 1 minus cos x times sine of x, all of that divided by sine x minus 1 sine x plus 1. Cos x times sine x will give me cos x sine x plus cos x minus cos x times sine of x, all of that divided by sine x minus 1 multiplied by sine x plus 1. Moving on from that step, Cos x sin x minus cos x sin x cancels each other out, so that leaves us with cos x over sin x minus 1 sin x plus 1 can become sin squared x minus 1, difference of two squares. Now let's take a look back at what we're trying to get to. We're trying to get to negative 1 over cos x. So I'm going to convert the sine squared x, I'm going to convert that into 1 minus cos squared x minus 1. That's going to equal cos x over 1 minus 1. I can just take the brackets away because there's no multiplying by the bracket. 1 minus 1 cancels each other out, which gives me an answer of negative cos squared x, which cos x and cos squared x will cancel to leave me with negative 1 over cos x, which is equal to the right hand side. Now the critical thing here was, once we simplified it, we needed a bit more direction. Always look back at the right hand side or at the other side. Look at where you are trying to get to. And that brings us to the end of the 4th tutorial on trigonometry. So far it is pretty easy. Go through the exercise that are left for you in the workbook before progressing on with the next tutorial.